In this lecture, we will discuss centralizer and normalizer. So first we start with the centralizers or center of a group. Center of a group. So for defining center of a group, so we take as let G be any group. G be any group and Z be defined as Z is equal to small z we take element of G such that Zx is equal to xz. For every x we also the element of G. So then Z is called center of a group or centralizer. Center of a group or centralizer. So we remember always. So that means suppose we have element. This is the group G and all the element, all the elements also belongs to G. So that means we remember the note. Suppose E be the identity element which belongs to G. So this identity always belongs to G because G be the example of group. The G be the any group, so E also belongs to G. So such that EX is equal to XE. Satisfy always for every X belongs to G. For every X belongs to the G cannot be empty set. Cannot be empty set. So it at least contain one element of G. So this XZ equal to ZX and Z belongs to G. So this is called the centralizer. So this is called the centralizer. So Z is called the centralizer of a group. So now we take one theorem related to this. So theorem statement says that prove that the center Z of a group G is a normal subgroup of G. Is a normal subgroup of G. Normal subgroup of G. So for proving this theorem, we take the definition of center of a group. So this equal to Z is equal to small z belongs to G such that Zx is equal to xz for every x also belongs to G. So this is our equation number 1. Now to prove that Z is a normal subgroup of G. Z is normal subgroup of G. Normal subgroup of G. So for proving Z is a normal subgroup of G, so we shall prove that Z is not equal to 5. So basically we start from this term. That means when we are going to prove any set is a subgroup, normal subgroup, so at least that set contain one element. That is the identity element. So we shall prove that Z is not equal to 5. So Z is not equal to 5. So we can write down as since Ex is equal to Xe. Ex equal to Xe for every X belongs to G. So that means this contain at least one element. That element is E belongs to Z. So then we can say that Z is not equal to 5. So hence Z is not equal to 5. So Z is not equal to 5. So then we prove that Z is a subgroup of Z is a subgroup of G. So for proving subgroup of G, so we take two element. So let we take Z1 and Z2, which belongs to Z. So we shall prove that Z1 into Z2 inverse also belongs to Z by the definition of subgroup. So now we use the definition of a centralizer of a group. So we can write down as Z1x, Z1 equal to Z1x equal to x Z1. This is our equation 2. This is our equation 2. Now second is Z2x is equal to x into Z2. So this is our equation number 3. So by using the definition of center of a group can says as Z belongs to Z, so then Zx equal to xz for every x belongs to G. So here we can write down as for every x belongs to G, for every x belongs to G. So now by using equation number 3, by using equation number 3, so we write down as z2x is equal to x into z2. So in this equation we pre and post multiply by z2 inverse. So we write down as pre and post multiply both side by z2 inverse. So here we multiply by z2 inverse. So we write down into z2 x into z2 inverse equal to z2 inverse into x into z2 into z2 inverse. So z2 inverse into z2, that is the identity ex into z2 inverse is equal to z2 inverse into x, or this also gives us identity. This also gives us identity. So identity ex equal to xe. So this can be written as x. Ex equal to x equal to x. So x into z2 inverse equal to z2 inverse into x. So now we can take this as equation number 4. So equation number 4. So this here is also we can write down okay, for every x belongs to G. So when x belongs to G, so it is clear by the definition of center of a group Z2 inverse. This Z2 inverse also belongs to Z. Z2 inverse also belongs to Z, because we know that when Z belongs to G such that Zx equal to xz. So here we shall prove that xz inverse equal to Z2 inverse into x. So that means Z2 inverse also belongs to G at Z. So now Z1 into Z2 inverse. Now Z1 into Z2 inverse into x. So this equal to, we can write down Z1 into x. So this can be written as x into Z2 inverse by using equation number 4. So we write down using 4. So using 4, so we can write down this as Z1 into x. So this can be written as Z1 into x into Z2 inverse. So this we can write down by using associative property, by using associative. So by using associative, so this equal to now we use the equation number 2 here. So here for this we use using equation 2. So when we use equation 2, so this gives us x into z1 or into z2 inverse. So x into z1 into z2 inverse. So we can write down this as z1 into z2 inverse into x is equal to x into z1 into z2 inverse. So x into this can be written as z1 into z2 inverse into x equal to x into z1 into z2 inverse. So xz equal to zx. So that means we can say that z1 into z2 inverse is belongs to z. So by using the definition of centralizer, so this z1 into z2 inverse is also belongs to z. So uh, general property we say that Z1 and Z2 belongs to Z, so which implies Z, Z1 into Z2 inverse belongs to Z. So this is for normal, sorry, so for subgroup. So here, so Z1 into Z2 inverse belongs to Z. So we can say that Z is a subgroup of G. Z is a subgroup of G. So Z is a subgroup of G. So now to prove that Z is a normal subgroup of G. A normal subgroup of G. So for proving a normal subgroup of G, so we take as let X belongs to Z and Z belongs to capital Z. So Z belongs to Z. So which implies that ZX is equal to XZ for every X belongs to G. So then we take as XZ X inverse. XZ X inverse. So this we can write down as this XZ can be written as ZX by using this into X inverse. So we write down this as in this form. So we write down this as into X inverse. So by using the associative, so this can be written the X into X inverse is identity. So this is ZE or Z into E equal to E into Z equal to Z. So this can be written as Z. So X Z X inverse is equal to Z, or this Z be the element of Z. So that means X Z X inverse equal to Z or Z belongs to Z. So that means we can say that if H belongs to H and X belongs to G, so X H X inverse belongs to H. So then H is said to be a normal subgroup of G. So here we see that Z small z belongs to Z and X Z X inverse. So this also belongs to Z. So we can say that Z is a normal subgroup of G. So Z is a normal subgroup of G. Z is a normal subgroup of G. Okay, so after understanding the centralizer, center of a group, so that means we follow Zx equal to Xz, X belongs to G, so Z belongs to Z. So Z also belongs to G. So Z is called a centralizer. So now we move to the next definition, that is a normalizer. So that is normalizer. So normalizer. So for defining the normalizer, we write down a let G be any group, G be any group, and A be the element of G. So then normalizer of element A, NA, is equal to X, which belongs to G, such that XA equal to AX. SA, XA equal to AX. So then A is called the normalizer. NA is called the normalizer. So we have some remark. So we also understand the remark. If we have NE, we have NE. So NE is equal to E. So this implies that XE equal to EX. So when we take as A equal to E, so as for every X belongs to G. So identity element, that means we take as E which belongs to G or G be the group, so identity element always exists. So follow the normalizer. Now, so when we can say that if G be an abelian group, so if G be an abelian group and A belongs to G such that XA equal to AX for every X belongs to G. So that means we can say that the normalizer of A is equal to G. Normalizer of A equal to G. Now, on the basis of this, we prove the theorem. So we have one theorem related to that. So prove that NA is a subgroup of G and normalizer is a subgroup of G. So for proving normalizer is a subgroup of G, so we take the definition. So by definition of normalizer definition says that NA equal to X belongs to G such that AX is equal to XA. So we take this as equation number 1. So for same thing, when we are going to prove subgroup of G, so it shall first we shall prove that this have any single element at least. So that means we shall prove that normalizer of A is not equal to empty phi. So since we write down as E belongs to G, but at least when G be a group, this contain at least the identity element. So G be a group, so that means EA is equal to AE. So it is clear that at least the identity element is belongs to normalizer of. So that means normalizer of A is not equal to phi. So normalizer A is not equal to phi. So now we prove that normalizer A is a subgroup of G. Is a subgroup of G. So for proving subgroup, so same we take two element x1 and x2, both belongs to normalizer of A. So then by definition of normalizer, we can write down as x1A equal to A into x1. This we can take as equation 2, and x2A is equal to A into x2. This is equation number 3. When we take two element of normalizer of A, so then we write down this. So by using equation 3, so we same thing we will do here. That means we pre and post multiply by x2 inverse. So pre and post multiply both side by x2 inverse. So here we take x2 inverse into x2 into A is equal to A into x2 inverse A into x2 into x2 inverse. So here we have this thing. Now we can write down this as x2 inverse into x2 by using associative. So this can be written as x2 inverse is equal to, we write down this as x2 inverse into A, or can be written as x2 into x2 inverse. So this x2 inverse into x2 is identity. So this can be written as A into x2 inverse is equal to this also identity x2 inverse into A. So this is our equation number 4. So this is our equation number 4. So it is clear that when we have Ax equal to xa, so that means x belongs to G, so that is it normalizer. So here x belongs to also normalizer of A. So here we can say that x2 inverse be also the element of normalizer of A. The normalizer of A. So then we can say that. So now we can write down x1 into x2 inverse into A. So this can be written as x1 into x2 inverse into A. So this is equal to x1 into A into x2 inverse. So this we can write down by using the equation number 4. So by using equation number 4, so this can be written as x1 into A or into x2 inverse. So this by using associative law, by using associative. So this we can write down as x1 into A can be written as A into x1 by definition. So into x2 inverse, or by using equation number 2. Now we see that we take the element x1, x2 inverse into A. So we see that A into x1 or x2 inverse. So this we can use by associative again. So x1 into x2 inverse. So this x1 x2 inverse into A equal to A into x1 x2 inverse. So by using the definition of a normalizer, so this element x1 x2 inverse also belongs to normalizer of A. Also belongs to normalizer of A. So we take two element, that means x1 x2, which belongs to normalizer of A, and we shall prove that x1 x2 inverse also belongs to normalizer of A. So it means that normalizer A is a subgroup of G. Subgroup of G.